G'day everyone, this is Haomaki Yingli and I'm going to be your Quantum Odyssey tour guide. And this will be the final live stream. Okay. G'day everyone, this is Haomaki Yingli, your Quantum Odyssey tour guide. I am very excited to announce that we are near the final orbitals of our descent, or let's say campaign mode of Quantum Odyssey. And the game should exit the early access around 2026, which is the mega FIFA World Cup. For the North American, it's going to be Dinky Die. It's much like a once-in-a-lifetime opportunity, much like the eclipse of 2024, the totality of 2024. And it also happens that I have decided to live stream this on the very Thanksgiving Day for you Americans. There's the other Thanksgiving on the Canadian side, but it's also called Columbus Day, and I'm very excited that we are able to finish the live stream by this year. So, Thanksgiving itself is one of the oldest American holidays. It's way back in the 1600s, and maybe because why it's late, but it's like, let's say it's the last Thursday of November. And below are the formulas which will be relevant for the third and fourth orbitals. On the top is a basic demonstration of phase kickback. Basically, phase kickback converts anything from in the state of 0 then negative into something that is the sign of that thing, even if you apply a controlled X gate. We can extend the idea of phase kickback using one of the unitaries against a bit string, which is encoded as an array of qubits, and then the minus state, which then, after kickback, it would still be the bit string and the minus state, but except the phase has been changed depending on the bit string value. The phase kickback algorithms includes the Deutsch-Josa and the Bernstein-Vazirani algorithm, and both of them are in the form X on the single ancilla, the H is on all, the unitary, the H is on the bit string, and then you measure the bit string and determine whether it is of one outcome of the other. Let's say balance versus constant for Deutsch-Josa. Bernstein-Vazirani uses the dot product and the XOR. This is an example of a Bernstein-Vazirani. And then we also have the Fourier transform, which is nothing really more than the speed of rotation, which is determined by the k, and then the contributions across all the output values of the base space, which is the x of the j's. And we have the ijk over there. And it can easily be converted into matrix form. Unfortunately, it is also unitary up to a constant factor. So let's say up to a constant factor. But there's technically a few variations, but we can make the matrix which represents how the Fourier transform is built into a unitary one, and there is a way to prove it. We will not go with the proofs. We're there to introduce this chapter with formulas to see what's the impression of how the formulas will be and how the formulas make sense with the last live stream. So over there we have f of the states, which is encoded as a state of, let's call it amplitude encoding of the f of x, which let's call this x of k, which then converts this into, let's say, this represents Fourier x of k. But we have to decompose this. Well, if the order is a power of 2, then we can convert this into a product of triangles starting with the h, and then the c, then rz gate, which is of successive square roots of the z gate, starting with, like, let's say t of 1 is the s gate, t of 2 is a classic t gate, control of that, and then we finish with a swap. So let's do the live stream now. We also notice that I'm also running on the development branch, noting that it is still an early access game and changes might be made, especially to the puzzles. However, I want to introduce that there is a new puzzle between the Civic Day and this Thanksgiving, which has not been live streamed. Namely, this puzzle is about the swap challenge. This is a new challenge that is not in the first version when campaign is still called Descent. So test your commands over invisible threads of logic. Have you longed to whisper a possibility into one qubit, watch it to collapse into certainty on another? Well, the swap gate is a variation of the X gate, so there's nothing imaginary going on, but ultimately it is a sequence of 3 CX gates of alternating rolls. I don't know where the 2-gate solution is, but this is not how we intend to solve this problem. We could cheat our way with an S gate, but S and then Z gate, okay. We can also cheat our way with a 2 Y gates, but this is not how to solve this problem. So you should not allow a Y gate. Okay, now we need to swap qubits ground and the second one. So qubit 3 and qubit 1 is to be swapped. So this one I don't think can be exploited using Ys. So we can use a swap on the qubit 3 and qubit 1. There is only one sigil on that is purely on the qubit 1 and the other on qubit 3. Now we have 4 sigils. So 4 sigils, however, notice that there's only one sigil on the that represents a pure qubit 4, pure qubit 3, qubit 2, and qubit 1. So it's now a permutation problem. We see that we need to swap qubit 3 and qubit 1. So we add a control over there. However, the way the C gates work is you cannot overlap C gates. Otherwise, we could accidentally create a Toffoli. Now we do the same for the qubit 2 and qubit 4. It doesn't matter how we alternate. We can alternate starting with the left or the right-handed, but it doesn't matter. This is because the swap gate is symmetric. There is a better solution, but this solution is not the topic of this puzzle. It might be suitable if we move this to the red path. Now we have the same again, except this time we swap qubit 1 with qubit 4 and qubit 2 with qubit 3. Okay. So we have a swap and then another swap. And this time we can do this in parallel. This is how the mystery gate works, because it does not see it as a C gate. Now we are doing pure amplitude encoding, so this time, besides switching the qubits based on their amplitudes in this state, we also have to correct the colors. So number 8 and number 9. Okay, so 9876. 9876. So now the first part is permutation. So 9 and 8 are displaced. So 9, 8. Now we have 8 and 6 are displaced. So which is going to be now the qubit 1 and qubit 2. Qubit 2 and qubit 3. So 8 is now going to take the role of qubit 4. So we have to swap this with qubit 2. Okay, however, we could do this in parallel, but okay. 9 is definitely in place. 9 is qubit 4, so that's the last one. 8 is qubit 1, so it's third qubit against the first qubit, qubit 3. So we can do another swap there. Now we have the amplitudes corrected. However, we need to correct the colors. Interestingly enough, we can just apply a S on the new qubit 4. So S over there. We can apply a Z on number 7, so which is a qubit 2, second qubit. 6, which is going to be the third qubit, qubit 1, which you need a ZS to fix. That means custom gates allows you to parallelize C gates as well. Now we have a 5 qubit case. So we have 6, 7, 8, 9, and then the 1 over root 2. This is the yin-yang, so this one needs to be moved to the 5th position. So it's qubit 3 to qubit 1. Okay, however, what you notice is there is a lack of a custom gate. So qubit 3 against qubit 1. We apply a custom S gate. So no, there's no swap gate provided as a custom gate. Now we have the qubits 4 and qubits 3 misplaced. So we also notice that the colors are wrong, so we can try with a Y. Okay, But this is an eigenstate of y, so it doesn't really work. Okay. Now we color correct the... Okay, so... Okay, it's gonna be the qubit 5 and qubit 2, so I got this thing slightly wrong. Okay, 9 is misplaced against 6, but 7, 8, and the root are correct. So we have this. Qubit 2, that's the third qubit, and ground qubit, qubit 5. You have to do it serially, because there is no custom gate provided. Now the sizes are all in order. The T gate, however, have to be placed after, on the ground qubit. On the fourth qubit, sorry about that, fourth qubit. There is another solution with only 2 gates, but this is not, again, not the topic of the lesson. We could try this, but it's technically not correct. Now we do the same with custom swap gates. Okay, so now we notice that the root is in the correct position, but the other 4 are not. The other 4 are in reversed position. So 6, 7, 8, 9. So 8, it will be changed positions from the second to the third. So second to the third. Okay. Now we have to change the new third against the ground. So the ground and the new third. Now we have to switch the second and the third. We don't touch the last one. And we do not touch the fourth, which is the root. Now there are these H gates that are trying to interfere. Do you think this would lead to something, let's call this, but it says if you understand swap, you will get this. Let's try, we take away the H's out. Disable the H's, then we operate the swaps in parallel. Okay. Namely, we need to swap the third against the first. Here's another example. We take out the H gates. Now we have the 8 against the 6. So, however, this is where the trick comes into play. Okay, so here we have, so this is where the trick comes into play. So we need to disable the H gates. Let's disable it over there to ensure that there's compatibility. Okay, so we have to swap the ground at the first. So swap. And another swap. Did you get it? Okay, so I technically didn't get it. Let's put the swap over there. So are we allowed to sandwich them between? Okay. So no, you cannot like sandwich these two. The last one is prove it, so let's apply a swap there, and then a swap there. And then sandwich that together. So let's see if this is gonna work. So this is gonna work. You can sandwich the swap between the edges. So it's 6 gates, there's a 2-gate solution, but that's more people under that. But again, this is not the topic of the lesson. Let's try disabling the unwanted gates with C. Now we apply the same swap. Okay, so now we have the let's swap the first and the third. Now we swap the last one, and then here we go. We padded with the C gates to simplify, but this is interestingly enough not the most efficient solution. Now let's continue to the classical side. So your computer runs quantum, and it does look a little bit tough. However, remember how there is an update regarding the how mystery gates work. But this time you need to understand what happens if we need to figure out this ourselves. What is A, what is B, and what is C? So let's say if A and B over there, okay, so if A and B are both off, then C is off. So I think this should be a half adder. This problem would likely be a half adder problem. Now if now we should add an OR. So OR of the first A and B to make C. So This problem, you're only allowed to use the logic gates. You are not allowed to use you're not allowed to use C gates for that exercise. So one, you try to let's half add with qubit 2. Let's half add again. And then let's finally half add once more. Now we have 2 H gates. Now it seems like you want to perform a 4 add or half add. So you're only allowed a half add or 4 add. Let's try a half add. Or 4 add. Okay. Can you add 2 superpositions? So how can we switch that? Okay. Okay, we can pad the first and the second one, so okay, so we have this. We have a 1. We need to add to set up the 1 over the sum. So 4 add. So 4 is the sum. Use everything to make it work. Okay, this is another example. This one should be easy. So 0, 5, 0, 5, but you're only allowed a 4 add or a half add. And we need to fill up all of these. So I think a 4 add might be required. We can use the second as a control, so we can also use the third as a control, so let's put the 4 add on the very front to see how it works. Okay, here's what we can do. figure out the B and the S. So we can ignore the 0 and the 0 and the 1 for now. So we have to fill in the 1 with an add. So full add. So now we have the 1 setup. We can now do it again. The 1 setup. And then we can use another full add. Again, a lot of things are by trial and error, so it's not it is hard for a reason. It's hard for a reason. Booted out of nothing. This could use like something called a ripple carry. This one, I believe it's hard because you need to understand how the half add works. How to swap positions. So, half add. So basically, it's determined by the ground at the second qubit. So I think we should try converting the A with the S. So if this is on, then this shall also be on. B would become an S, the C would stay as is. We don't look at the top qubit. Let's do the full add. Let's try if this approach is going to work. The full add might work. But these are the only two gates we are allowed to have. So can we try like another example? So let's try multiple half adds. Now, okay, now here we have it. So 101. Let's try another half add to put it to the correct position. So now we want to do this. B becomes S. However, the C will then be turned on. So we are not allowed to like discard this either. So because if 2 are there, we could have like all 3 are there. So let's try taking out 1. Now all 3 are present. Now we want to take out the other 2. So we want to use the one wants to take out. Okay, A would stay as is, B would stay as is, but C, the sum would be gone, and then the S would be gone. So let's try a full add. Now we have 2. Okay, so now we should have the solution, the first part of the solution. The next part of the solution requires an A. And if this happens, we can set up the rest. So we can now do the half add. And this is our solution on the right hand side, using the top qubit as the A. The last problem is nothing more than turning all of them inside out. First, we can set up a NOR, technically a NAND. So NAND would be there enough to like promote this to a 1. But after that, we need to turn off all of them on. Okay, then there is a full add. Interestingly enough, this one skips the full add. So let's try using an OR. So A or B over the A. Okay, now we have like a shortcut. We have a shortcut. Let's try an OR and turn on the right. And then we did this with only 3 extra gates, just by eyeballing that end. And we finished this with only 3 gates. I was on bracket 5. Now this is still not an easy one to deal with. We will now focus on the challenge electrons of the 3 phenomena problems. The first one is the kickback. I checked out, many of them have like this one is reversing without an X, so you're not allowed to use an X in this case. What you can do is you can make a ghetto version of an X. So let's call this Z Z. We use Z, we use an H, then we use CZ, and then move back. So here is a solution, which is the kickback formula. Notice the X and the Z rows have to change. Okay. This is an example of a Grover's diffusion run. So let's try running the same thing again. So again, many of these problems, I noticed the swap has shortcuts. So let's shortcut that. But the actual answer has 4 gates, so this is an example of a shortcut. Kicks the faces. Okay. Thoughtfully through faces and a random uneven superposition. So this one looks like a generic Hadamard. So an entanglement. So we perform an H, perform another H, and then we perform control. We control that, and then we. Okay, there is an S gate over there. Z over there, so then we have a control gate. Now we do this there, and then we do a CX. There is a. Maybe I am using a shortcut to solve this problem. However, the actual version of that, we will explain this in detail outside of the live stream. They will be revisited. So CX. Okay, we are not allowed to CX that. So we can do is we can ghetto a CX. Make a ghetto version of that using CZs. Okay, now we have a random uneven superposition. This is not this one is going to be tricky because it forces you to create an eye. So here we split this. And you're not given a custom gate, so let's S gate that. Let's try a T. So the T might be a tip. Then we perform another CH. Okay, so now there might be a solution. So let's go with CY. Let's do an S over there, and then we need another S on the right half. So Z on the right half. So here we use an T-gate. But again, a lot of these solutions are likely, let's say, ghetto ways of solving the challenges. Bernstein-Vazirani challenge, the optimal one is the one that matches how it's intended to be. This is probably the easier of the three, so you can just use an H. Okay, so now we have the X. Let's say the X is that pivot, the other register. We can just add an H. There is a shortcut on solving that. Now remember this pattern. So CX. Let's call this the X qubit. Okay, this one has the same idea. The H is broken, but we will have to use 2. So same thing. So this one, once you remember the pattern, it should be easy. So this is the intended solution. Maybe we could like use it without X, but again, this is early access and the puzzles might change. I will explain why there sometimes is a shortcut and whether the shortcut defeats the point of the puzzle. This is the 1 qubit case. The head of each of these triangular operators is the H gate, and then it's the CT gates. This is nothing more than XH, X. This is the 2 case, so we have X, the first triangle, the H is over there, but okay. We are now tasked to reverse the Fourier transform, and the I gates are there to prevent any ghetto attempts. So we have Z, we need the opposite of the S gate, and then perform the H. This is the proper way. Now we have the 3 case. So H, T, S. H, then S. The smaller one, then the next one would logically be the 3 qubit reverse without cheats. So you're not allowed to cheat your way. So we cancel out the H. We C, S, that. And then we do the same. Which is going to be SZ, T, S, Z over there. And then we can just add a second X. However, this is a rather ghetto method. I don't know if it's like the intended solution, because it says no cheats. So I'm doing it just as they intended. The cheat way is to just use T gates. So T gates. Notice that we have like a progression. qubits, but ultimately you still have to swap. There is no swap in this puzzle, so we also are not going to explore the fourth of the Fourier transform, so the 4-qubit Fourier transform or the 5-qubit, but there likely will be, possibly in the challenge, maybe. We will move on to the red path, the 4-qubit system preparation. This is nothing more than an easy bell state called the GHZ. The other one is another easy bell state. We can perform. We can do this. We can divide it into halves. Then we can shift it internally. Now, this is where the trick comes into play. We may need a swap, so called a Fredkin. So we perform a Fredkin on the first and second qubit. So Fredkin. Okay, this is not a Fredkin, so we just change the okay, this is a Fredkin. This is a Fredkin. In fact, this is a Fredkin of a Fredkin. Let's say controlled Fredkin gate. This is another easy GHZ problem. GHZ. We can also use XZ. We do an X. We perform a Z or an S, and then it's perform the GHZ. We can also do that with using a Y as well. We can just save one gate. We can save another one. So this is an optimal solution. Okay, this one is another easy C gate problem. Okay. This is a C gate. We just add another S over there. So, interestingly enough, the 4-qubit the 4-qubit one is probably the easier of the two. Okay, this one would require a T twist, so let's do a T. But however, we will also need another T side as well. You just have to then add another Z, S, T. This is a brilliant solution. Okay, I'm actually probably the first one to have this brilliant solution. This one, we need to forge an algorithm, sequence so precise it can be etched into a single extraordinary gate. Okay. There is an RX gate, so we can just split this on the H gate on the second. But we should first perform X. Then we should do a CX, do a CH, so CH, CH. Okay, now we should have something now easy. So if both of the lowest two qubits are on, we apply an X, and then we now apply a double Y to switch it back. The best one has 8, I have saw 7. Prove to me that you're worthy to step beyond the threshold. Okay. Oh, but then the gate will yield to the will. Okay. So here's the problem. We want to take out the S. Then we have the W state. The W state over there, and we need to find a way to reverse that. Okay, we can disable the... Okay, it does not... We have to use the W. We have to use the W. We have to use the W. I don't think like the W can be, you can run away from the W's. Okay. So here it is. You cannot run away from the W. The W state will flip this thing out. There's an X as well, so can we try to use the Y's to resolve the... three-way division? Okay, here's the thing. We need to merge the 3. So let's say if this is on, we can perform a merge. Now, if this is on, okay, so here does it not quite work? You cannot, let's say we even superposition that. Let's try this. Okay, now it's starting to yield. So, but here's a problem. We need to shift this thing up. then we need green. So we have the green. So we have this. We have to X them all. Advance. So now we are nearly done. Okay, so we are done now. So this is an above average solution. Okay. Listen, this is my final gift to you. The moment I have long awaited mastering quantum isn't about formulous memorization. It's about breaking free from every illusion from the change of mind. Remember this. If there are quantum medicines woven the very threads that shape existence is your birthright, law written into the cosmos yourself. This is one of the later quotes. So you are prime a sage. The God key is already within your grasp. So this is the God key. And it's okay, sorry if there's a reverb. The God key. This is the other impossible puzzle. So we have our second one on the fourth ring. This is the You're Ready's older brother. So it now has the spaces are narrow. There are like HC gates. And then you have only like 1 hour to solve, or else it will reset. But again, the idea is quite similar. Holy shit. I think there must be like some recent changes to the God key that makes it even harder than before. We can try using the C gates to take out those which we do not want. We can add an H. We can add an H. But it now makes it much more harder to read. We can use another H. This is where the trick comes into play. Now we have all the colors. And you cannot escape. So basically, God key, I notice it has been made harder. I believe. I conjecture it has been made harder. Try using as control to take out. Okay, now we only have a Toffoli. We can skip that. This is easy.
now the colors are the same. We can take out. We actually can take out many of these gates to skip large portions. Now we use an H. Again, so now the problem becomes much more trivialized. We now have two yin-yangs. We can use the S to make the colors the same. But you can use the H, and we can use another H to cancel out. We can take out the T. This is when things get easy now. So H. This is when the multiplication comes into play. Okay, so this doesn't look good. So we want to simplify this with a Y. And then the H's. Okay, these are we apply 5 Grovers in a row. 5 Grovers in a row. So how do you deal with these 5 Grovers? Take out the H as well to simplify. Now the Grover will not work against you. Now it's the H. Okay, so the Grovers, the 5 Grovers applied have let's check the tensor vector. So let's do the advanced view. So 0.5 and 0.5. They're to be moved and they're to be merged. Okay, let's see if any of them fixes up the Y gates. Okay, here is a hint. There is an H gate, HC, which could equalize the stuff, but you're not allowed to use HC. Let's try the H to see if this is going to fix up. Okay, now we have a combination that looks very much like we could flip, then we could merge. Okay, the only thing is now we have to put this out, then we could use C's to put it back to where it belongs. C. Let's try SX if this is going to work. Don't think it's going to work. Okay, you cannot HC the thing. Let's see if the X's are too much. The H's are too much, so we have to flip the script. If all three are there, we can merge. Because there's an unusually small member, there is a YN as well, but I think we need to rest because this puzzle has changed. So I know so far this puzzle has changed. So 18. Let's merge this again. So this can't be right. We have to, because they're all on the right, so we merge them together. One, two, three, four, five, six, seven, 8, 9. So there are, it actually splits into 9 parts. So there must be like a slight anomaly. Okay. here's a possible issue. Maybe like we have to split this into cannot split this into 9 parts. We have to split this into 8 parts. 1, 2, 3, 4, 5, 6, 7, 8. But I ended up splitting into 9. So this, the reason is it's because of an H gate. So we need to take out the H's off. One, two, three, four, 5, 6, 7, 8. So now we should be able to finish the puzzle. I, 4 I's, 142, then we should have a 2. Okay, so we're nearly done. 201, then we need to move one thing now. It's now just moving the terms. Up. There's a YN, so we need to address that. 201. So here we have solved the God key in 15 minutes. Strange Odyssey. And interesting enough, I'm one of the worst in this percentile, but this puzzle has changed. It used to be easier when I looked at Molygnacius' solution. And there we conclude our Thanksgiving holiday. We conclude our Thanksgiving holiday. And here we conclude our Thanksgiving holiday. I hope you enjoyed the live streams. Please remember these live streams will eventually be manually chaptered. None of the episodes use any part of generative AI or AI summarization. They will be reorganized and the unfavorable parts will be cut out. I wish you the best of luck of your winter holiday if you're American, or summer holiday if you're Australian, and happy 2026. Enjoy the Olympics and enjoy the soccer rules.